All right, so we're going to change gears quite a bit here from the fish tank and the salt and sinking, and talk about north-south flight. So one thing that always bothered me is plane travel on the ball. And there's a lot of talk about northwest, or I mean, sorry, east-west, west to east, and going with and against the spin of the Earth, but not quite as much talk about going from south to north and north to south. And I always thought that that was one of the ball's Achilles heels, was the fact that there is what is it called? It's not the spin of the Earth, the axis is different. So that would be one of the big differences between a spinning sphere and a flat circular plane with rotating celestial objects above it, would be the spin. So I started thinking about this, and I am going to talk about one plane flight in particular and ask a couple questions about it that I hope I can get an answer to, because I think it's a pretty interesting case. So obviously we know all about what we're told about Coriolis. This shows the north to south flight and what would happen theoretically for a projectile that went from the North Pole to the equator in 1 hour. It would deflect about 15 degrees. Essentially. So as you're moving south, the Earth is moving counterclockwise.
Are you changing? Are you on screen one at the minute?
No, it should say the effect of Coriolis force.
No, it's not changed over. So we've not seen that. You have to switch.
Oh, shoot.
It's kind of frozen. There we go. We can see that now. Yeah, perfect. Right. Okay. I'll go.
All right. I'll just leave it right here then. Maybe it's having a problem with the rendering or whatever. All right. So we've all seen this before. So as you move from north to south, you're losing momentum. Your momentum that you gain from the spin of the Earth is less than the momentum at the location as you get further south. So you're falling behind the Earth, essentially. This is what we're told. And you can see here for the different latitudes, I'm just talking about the northern hemisphere here. The speed that we're told that the Earth rotates, the ground speed of the Earth at that location. So at 90 degrees, obviously the North Pole, we're at 0. And at the equator, we get up to 1,038 miles per hour, or 1,670 kilometers. And just for the sake of making this simple, I'm going to talk about in miles per hour for the rest of the presentation. Sorry to all the metric folks out there. All right, so I think most of you are probably pretty familiar with this, but if not, you can easily look it up. And then, of course, there is a number of miles that each, the distance between the longitude line at those areas. So the Earth's getting fatter and faster. All right, the flight we're going to talk about today is from Anchorage, Alaska, in the United States, at 60 degrees north latitude, to Mexico City at approximately 20 degrees north latitude. And we're talking about a specific flight, an actual flight that happened called Cathay Pacific 86. And this happened on the 22nd of July. And it took about 6 hours and 54 minutes to make the trip from Anchorage to Mexico City. And here you can see the latitude and longitude. For the sake of simplicity, in most cases, I've used 20 degrees and 100 degrees for Mexico City, and 60 and 150 for Anchorage, Alaska. It's not going to make that much of a difference to the analysis. This is the plane that we're talking about. Not that it makes a lick of difference, but its max speed is 570 miles per hour. It's a Boeing 747-8. Its max altitude is, in this flight was 31,000. You can see the distance that it went, about 3,800 miles. Yeah. Okay. And this is what it looks like in FlightAware, the path. So this is the actual flight path that they took. Same as what I showed on the map earlier. And you can see their latitude and their speed here, or their altitude. All right. So one more time, this is the flight. This is the specifics for the flight. Their average speed was 544 miles per hour. They went 3,755 miles. I'm going to walk through this flight leg by leg and talk about it on a rotating Earth. The view you're seeing right now is what it looks like on a stationary sphere. So Obviously, it's going to look different. And what we're going to do is we're going to hold this steady. We're going to call this 0 point, let's say, okay, 0 degrees. And I'm going to rotate in each of the following pictures for the amount of rotation that takes place on the spinning ball Earth. And we're going to trace out the actual flight path through space and talk about the speeds through space that would be required in order to make this flight. Hope that makes sense. All right, and here I'm just showing that the Earth is rotating this way. Now, the whole duration of the trip, the Earth is going to rotate quite a bit. So Mexico City starts off here, if you're looking down on the top of the Earth, and ends up down here. Okay, so actually, if they were flying from here to the location in space where Mexico City ends up, their great circle distance would be somewhat like this instead of like this, just to give you an idea of the difference that we're talking about. It's pretty drastic. Now we're going to go through step by step. First waypoint is obviously Anchorage at 60 north, 150 west. Our second waypoint, we rotated at about 31 degrees, is at 50 north. So there's going to be a waypoint at each latitude line that we cross down to 20 degrees north latitude. This took about 2 hours, and they went 2,212 miles through space, and their average speed in space was 1,079. Now here I've got to talk about the momentum that they supposedly inherited from the spinning Earth at the location that they started. So in Anchorage, roughly the ground speed of the Earth is 513 miles an hour. So what we're told is this plane sitting on the ground and everything on the ground in Anchorage is rotating at 513 miles an hour, and that's going to add up to a 24-hour day, and they're going to go around their great circle distance of 12,303 miles an hour. So it's just 12,303 divided by 24. So when we talk about how fast the plane is going in this presentation, we're talking about the 513 miles an hour that they inherited from their starting latitude, plus the speed that they accelerate due to their engine or other factors. Okay. All right, let me go down here. This is the one we left off of, this waypoint 2. So that probably makes a little more sense, the 1,000 miles an hour. So it's 513 plus the speed of the engine. Third waypoint at 40 degrees north, the Earth has rotated another 23.5 degrees. This took an hour and a half. And the miles that they traveled in space was 1,762. Their average speed in space increased to 1,125 miles an hour. And you can see that their path is starting to arc here. And this is kind of a familiar pattern that you've noticed, because this is how they say that Coriolis looks. Maybe not so drastic, but this is the general direction. Okay, fourth waypoint, 30 degrees north. Took another hour and a half. They went another 1,700 and some odd miles, and the average speed was 1,179. Another increase, another rotation of 21.75 degrees. And the destination, when they finally arrive in Mexico City at 20 degrees north, another hour and 50 minutes. They've reached the elapsed time for the flight, 27.5 degree rotation of the Earth. They went a whopping 2,499 miles in space on this last leg during the last hour and 50 minutes of the flight. And their average speed increased drastically to 1,363 miles an hour. Now remember, they've inherited from their starting location 513. So if you subtract the 513, the engine would theoretically add to their acceleration and their speed about, 850 miles an hour. So their total flight through space, you can see it all added up. The Earth rotated 103.5 degrees. They went 8,183 miles through space, as opposed to the stationary measured distance of 3,755. And their average speed was 1,186 miles an hour. Now, just to contrast this with the return flight, going from Mexico City to Anchorage. This flight happened on the 25th. It took nearly the same amount of time, 6 hours and 57 minutes. It's almost the same distance, and their average speed was 540 miles per hour. Theoretically, on this return trip, they're inheriting the momentum. They're at a greater ground speed at 20 degrees north. From that, being closer to the equator, their speed that they inherit is greater, and they're going into lower speed, so they don't have to catch up to the Earth. So the actual geodetic distance is almost equal to the distance that they traveled through space. All right, now I'm going to get to the questions. I hope you guys are following. Question number 1. The flight covered 8,183 miles in 6 hours and 54 minutes. Its average speed was 1,186 miles an hour. At 60 degrees north, they inherited 513 miles per hour in momentum on the plane. Probably used the word momentum wrong, so I'll hear about that. In order to meet the reported and required ground speeds at each waypoint, the plane must increase its speed in space. During the last leg of the trip, the plane's engine must provide an average of 850 miles per hour worth of power in order to accelerate to the 1,363 miles an hour that they had on their last leg of the trip. Is this correct? Why or why not? And I'll just point at what I'm talking about here. These are the adjusted geodetic distances, the great circle distances for each leg of the trip. This is their required speed. So as I showed you earlier, it increases for each leg of the trip and then drastically increases on the last leg. The momentum that they inherited, or the speed that they inherited, and the required engine speed that they had to make up. So they had to increase their speed in order to catch up to Mexico City, essentially, as they went south. And they, at the end, they were adding 850 miles an hour to the speed that they inherited. How did they do this? Is this correct? Why or why not? Question number 2. The route taken for the flight isn't the optimal route. It is the geodetic great circle route based on a stationary Earth. This is the route that you would plan if we were on a stationary flat plane or a stationary globe, essentially. Why don't the pilots of the flight take the rotation of the Earth into account when planning their flight and go a different heading? Why is their flight path the same as it would be on a stationary Earth? So the optimal flight plan, if they were going from one, would be something like this. But really, their flight plan would probably be somewhere in the middle. They'd actually go at a different heading, not head straight towards Mexico City, so that they can, optimize their arc in space. I didn't calculate that would be, but I assume it would be like. Question number 3. Since the return flight from Mexico City to Anchorage can take advantage of the additional momentum imparted by moving from greater to lower rotation speeds and into Earth's rotation instead of against it, the total distance in space and engine effort required is significantly lower. The geodetic distance for the return flight is 3759, equivalent to the stationary Earth geodetic distance. Do pilots account for these differences in their flight plans? Meaning, do they account for the fuel requirement differences from going south to north and the distance that they travel through space and the increase in power that is required for them to gain momentum? Does anybody have any evidence that any of these considerations are accounted for when estimating fuel requirements for north to south or south to north flights? So those are my 3 questions, and there's a whole bunch of other considerations that I didn't even get to yet that I want to see what people come back with and then address. Because the heading of the plane when they arrive at their destination, for one, is going to be different in each model. On a stationary plane, it's very simple. You fly towards your destination, your plane is heading that way, you adjust for the wind, etc. In this rotating Earth model, you're going to have momentum in one direction, and you're going to have to try to either decrease the momentum in that direction or increase the momentum in that direction, and that direction does not equal the direction that the plane is pointed. It's essentially a crosswind that is required, or a cross momentum that's required in order for you to catch up or slow down to the Earth. Now, planes are capable of adjusting for crosswinds and winds, but I'd like to know how that momentum is transferred to the Earth, or how they decrease their momentum when they're going from south to north. Doesn't make any sense. We never hear about accidents because pilots didn't take these things into account. We never hear about pilots talking about these. We never hear pilots discuss that they're going either north or south and how their flight plans were different. These are not considerations that I have ever heard in my life people talk about outside of Wolfie in his video with his wife. So I'd like to have some answers on how this is possible. And I've already gotten some previews of what that'll be, which is essentially the wind makes it happen. And they adjust slightly, inch by inch as they go along. That doesn't add up. You guys are breaking your own laws of physics. So let's hear it. Thank you. That's it. Thanks, Ranty.